All right, so here's an example. This example is, kind of based on what we are looking at together in the stats lab. You know that the digital wellness survey looks at optimism before and after the campus shut down because of COVID. These numbers, however, are just made up. Okay, so don't think that these are true numbers. They just popped into my head. But let's say we wanted to look at optimism before and after the campus closed because of COVID, and we used the optimism scale that I developed for the survey, and I believe it goes 1 to 6, I want to say. Could be 1 to 5. Either way, we looked at optimism before, and let's just say that the mean of the people who took the survey before COVID was 4.56. And then we looked at optimism in a separate group of people, but it was after the campus closed, and it dropped to 2.22. All right. Now, these are both estimates. This is estimating mu, right, the mean of the population of the, let's say, students in general before COVID. So this is an X bar, and it's an estimate of mu for the population of students before COVID. This is also X bar, but a separate population. This is a different group of people. So this is the X bar, the mean of the sample that is estimating mu for all the students after the closure of the campus. So for each mean, we're going to calculate sampling error. So with this one, we need to know the standard deviation of the sample and the sample size, but once we have that, we do the calculation, and let's say it comes out to be 0.23. This one here, we do the calculation, and it comes out to be 0.35. So we can see that the estimates of sampling error are different for our two different samples. This one is higher. So if I ask the question, which mean is more accurate? Probably. Okay, it's always going to be probably. Which sample mean is probably closer to mu? Which one is probably more accurate? And then how can you tell? Well, in order to answer that question, you have to look here. And you say, well, wait a second, this is a smaller number. This is reflecting less error. So that means that this mean is probably closer to the population mean than this one is. This X bar is probably closer to the population of students before the campus closed. This sample mean is probably further away from the population mean of the campus or the students after the closure. So this means probably more accurate than this one. And it all has to do with this. Okay? The smaller the number means less sampling error, and it means that your X bar is probably a better estimate of mu. Now, one thing that is going to come up is how can you tell if, by looking at an SEM, how can you tell if this is big or small? You can certainly, if I ask you which one is bigger, which one is smaller, well, that's just kind of like a duh, right? You just have to look at these numbers and say, this is small, this is bigger. But let's just say that you only had one number here. Let's just erase this, okay? Pretend this isn't here. So now let's say I give you this number, and you know the mean, and you know this number, and I say, do you have a lot of sampling error or a little bit of sampling error? How are you going to answer that question? The answer is it's all relative. So 0.23 is relatively small compared to this number, right? If you were to look at this, it would be relatively small. So I would say, okay, relative to the mean, it's a small number, so we don't have a lot of sampling error. What if this were 2.3 instead of 0.23? If this were 2.3, we would say, oh my gosh, well, that's getting to be pretty big, right? 2.3 could just be a score in the data set, right? If you have a mean of 4.6, you probably have some scores that are a lot smaller, a lot bigger. So if you had a 2.3 for your SEM, that could be even a raw score here in this sample. So 2.3 would be large compared to the mean, and we would say SEM is big. All right. So one method of deciding if SEM is big or small is to compare it to the mean. If it's really, really, really small compared to the mean, that means your SEM is small. And if it's, about as big as the mean, or could easily be a score in the data set, then you know that your SEM is large, right? So if it were 2.3, we would say SEM is big. So it's all relative. Another way that you could do this, let's say you didn't have the mean. Another way you could do it is look at all your raw scores. All right. If all your raw scores, let's say your SEM is 0.23, and all your raw scores are like 0.60, 0.28, 0.95, 1.2. You see how 0.23 could easily be a raw score in that distribution? Then we would say this is huge, even 0.23. If all your raw scores are around this same size, then that makes this really, really big. However, if I said your sample, the scores in your sample are 16.28, 19.65, 11.5, 12.2, then 0.23 is much, 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 much smaller than all the scores in your sample. That makes this very small. So again, it's all relative. All right. If I were to give you a question and say, is 0.23 for an SEM, is 0.23 big or small? And I didn't tell you anything else, then you'd have to say, there's not enough information to answer the question. You have to at least know the mean in order to see relative, is it big or small relative to the mean? Or you have to know what your data set looked like. All right. If your data set has scores all around this size, then this is going to be huge. If your data set has really, really big numbers in it, then that makes this really small. Okay. Now, whenever you are answering a question about is your mean accurate, your X bar, how accurate is it? You always have to include the word probably, because we don't know for sure. When we calculate SEM, we're estimating SEM, right? You remember that? We're estimating sampling error. So when we calculate an X bar and we estimate sample size, all we can say is, well, X bar is probably good, probably bad. We don't know for sure. Remember, when you sample, there's a lot of uncertainty. You don't have all the data. And I just explained why.